Welcome everyone. So today we're going to be talking about probabilistic inference models in AI. Very fun lecture, very short lecture. We're only going to be covering some very introductory material here and follow that up with other videos, okay? So why do we even want to study this thing? Well, first of all, see, we have already studied the searching problems. We know uninformed search, informed search, A-star, adversarial search, alpha-beta pruning. We've also studied constraint satisfaction problems, including AC3. We have also handled uncertainty, such as MDPs, and reinforcement learning, where we don't even know the transition model or the reward model, right? However, one thing that we are still missing is reasoning about uncertainty when an observation is made. So when we make an observation, our sensor makes a reading. How do we update our beliefs? What can we say now that we couldn't say earlier? That's why we study this material. So within that, today what we're going to cover is some very basic definitions, basic concepts such as uncertainty, random variables, probability distribution, and events. And in follow-up videos, we'll talk about marginalization and some of the other more useful ways to use those concepts here. So as a very basic definition here, uncertainty is when there are some variables, so agent knows certain things about the state of the world, and there are some unobserved variables for which we need to reason about. So the agent does not really know where the location of the adversary could be, or if this particular part is really faulty or not. And the model knows a little bit about the connections between these variables, and when an observation is made, then the agent needs to make an inference and then be able to use that particular newfound knowledge to the best of its capability. So this is what we refer to as probabilistic reasoning. It's a framework for managing our beliefs and knowledge. Okay. So let's start by giving a definition here, which is for a random variable. A random variable is any aspect of the world about which we have some uncertainty. For example, is it raining? Is it hot, cold, warm, lukewarm, etc.? So those can be represented by random variables R or T. Similarly, driving time, location of the adversary, etc. As a matter of notation, we generally denote the random variables with capital letters. And just like in constraint satisfaction problems, each random variable has a domain. We write them generally with the lowercase letters. So for example, raining, if we're asking the question such as, is it raining? Then the domain could be true or false. But if it's saying temperature could be hot, cold, warm, etc. So the domains can change, and depending upon the random variable itself, we can have a different domain for it. Now we come to the concept of a probability distribution. Under the probability distribution, we associate a probability with each domain value, saying that, okay, for this particular domain value, this is the probability, etc. So for example, for temperature, the random variable temperature, we say that the domain being hot, the probability is 0.5. The domain being cold, probability is 0.5. Similarly, for weather, we say it's sunny, rainy, foggy. These are the probabilities here. Okay. Even the unobserved random variables have some distribution. We may or may not know about it. Okay. If we know about it, we can certainly use that. And if we don't know about it, that means we still have to infer it. The distribution is a map, or in other words, a table of each particular domain value with a probability. And the probability is a quantitative value. If we are just looking for one particular domain value, we would just have a probability. But for the entire table, that means for all the domain values, we'll have a map or a table represented like we have here. So a probability is a single number. Distribution is a table or a map. Now, two simple concepts about probability still apply. That probability values are positive greater than equal to 0, non-negative, and the sum of probabilities for a particular random variable need to add up to 1. So that means these two equations are still relevant and still valid. We come to a shorthand notation. Sometimes we can use a shorthand notation, such as in this case, probability of heart is equal to probability of t is equal to heart. This is fine as long as you have each domain value is unique. Now, if you have 5 random variables, all are Boolean, true, false, then you couldn't say p true because you wouldn't know which one is equal to true. In that case, you would say p x1 is equal to true. So you are welcome to use the shorthand notation only if it does not cause some ambiguity. Now, coming from a single distribution, you can also have a joint distribution. That means if you have 2 random variables or 3 random variables, or in general a set of n random variables, then, and it's not a set as in it's unordered, it'll have to be a tuple still, then in the tuple, the joint distribution specify a real number for each assignment, which we shall refer to as each outcome. That means one domain value per variable. So px1 is equal to x1, px2 is equal to x2. So this is the outcome, and this is one assignment. And for that particular value, we will have again a probability value, which again needs to be non-negative. And the sum of those values for all combinations of those random variables again needs to sum up to 1 here. And in this table, you can see a very tiny example of 2 by 2. That means a total of 4, a table of 4 different values here. So we can say hot and sunny. The probability of that is 0.4. The probability of hot and rain is probability 0.1, etc. Okay. Now the question is, what is the size of the joint distribution table? It is generally impractical to write it out. Let's suppose you have n variables and domain size d. What is the size of the distribution table? Is it n times d, d factorial times n, d power n, n power d? So what is the size of the joint distribution table? Well, one way to think about it is that let's consider x, the variable x, the random variable x. Then we have d values here. For each of them, we will have, again, d values of y. For each of them, we'll have d values of z, etc., etc. So that means d times d times d times d, which points to this answer, d power n. Okay. And if the domain values are different, then it'll be d1 times d2 times d3 times d4. They don't need to all be the same. If they're different, we just multiply them. As a bottom line, the size of the joint distribution table is too much. You have 20 variables, each with a domain value of 10. That's 10 power 20. So it's not going to be held in the RAM. You can probably write it out somewhere in a large database or a pattern database, etc. But it's not going to be a small map that you can hold in memory. So the size of distribution makes it the joint distribution normally impractical to write out. And that's why in one of the further videos, we will talk about marginal distributions, etc. The event, which we already discussed a little bit, is the set E of outcomes. So we're given outcome, and that's the set of that is the event. From a joint distribution, we can calculate the probability of any event. So if somebody were to say, what's the probability this hot and sunny? Well, that's just hot and sunny, that's 0.4. It's hot, then we will take the sum of these two because both of them correspond to hot itself. This actually is a marginal distribution. So the hot is then 0.5. The probability that it's hot or sunny, that's 1, 2, and this one. So that's together 0.7. So typically, the events that we care about are partial assignments. That means when the question comes, usually a business question comes, the question does not usually ask us about a joint distribution. It usually asks us about a partial assignment, a marginal distribution. But what we have covered here gives us a solid start to be able to do those things. Here's a very tiny quiz. You already know some of the answers here. What's the probability of plus x plus y? Well, that's only one matching row here, that's 0.2. Plus x, that has two matching rows here. 0.2 plus 0.3, that's 0.5. Minus y or plus x, well, let's look at these ones. So we get 0.6. So given a joint distribution table, we can compute this trivially. There's no question. The bigger question, though, is the thing to remember is the joint distribution tables are normally not available. They're normally not going to be available because they're going to be too memory intensive. So that's all I have in this particular video. We have just talked about definitions, basic concepts. We will still talk about the other material, but this is where we can start talking about the overall concept of probabilistic inference and how we can use that to our advantage.